Good morning. What makes us human? This is the question that the Friar, in his article that I'm presenting today, is going to ask. He notices that human beings have evolved to like things like conspicuous consumption. In a sense, all societies seem to have this feature of liking conspicuous consumptions, and the Friar argues that this is because it is hardwired in our brain, in our behavior, in our psyche. But the question is, what is the evolutionary advantage of such a preference? The next 3 slides present the question that the Friar asks in his paper. Consider activities like liking sugar and fat, being fearful of snakes, and being able to throw projectiles accurately. The people who could do this thousands, millions of years ago survived more, and therefore their genes are present in our genome today. Today, even if there is no particular survival advantage, we like sugar and fat, even though that's actually a bad thing. We fear snakes, although many more people are killed by cars than by snakes today, and we can throw a cricket ball pretty accurately, which, though useful, doesn't really help survival. Today, we like things like expensive watches, cars, wine, and so on. So why is it the case that the people who like expensive, useless things, and I put expensive in inverted commas because expensive means things that could put your life at jeopardy, like wearing the teeth of a saber tiger, or napping stones, hand axes they're called, in a very nice looking manner. Napping stones was very dangerous. First of all, it took time. Second, you may actually maim your fingers or your eyes, and that has a huge cost in terms of survival in the savannah, where being able to see properly was very important. So why is it that those people who like those things passed more genes to us? And then the Friar translates this question into the language of economics. The things we are taught when we come here in the first year, the utility function that increases with consumption, the preferences, where do they come from? There is a trade-off between survival and non-survival activities. Eating, having shelter, that helps our survival. But why driving a Ferrari? What's the good of why do we like it? Why are we prepared to spend resources, valuable resources for survival, in order to buy a Ferrari or things like that? So the question, what are the evolutionary advantages of trading survival activities off conspicuous consumption? The answer that the Friar gives goes back to Darwin. We all know Darwin about his sentences, his catchphrases of survival of the fittest, but it was more subtle than that because he had 2 points to make, well, amongst many others of course. He talked about natural selection and sexual selection. The point is, surviving is useless unless you mate, unless you have genes. You have a way of passing your good genes, the genes good for survival, to the next generation. And so there might be activities that, although they're costly in terms of survival, they actually give an advantage in terms of reproduction. And what the Friar says is that consumption is one of those. The trade-off between survival activities and consumption is sexually selective. Just like the feathers of a peacock, which are actually a very bad thing to have in terms of survival. The point is, a male, an early human male who liked consumption, put himself at a handicap because he had to take activities in order to display this consumption, which reduced his capacity to survive. But the fact that he had survived despite all this implied that he had passed the test. So a female who chooses only those males who have passed the test as mates is joining her own genes to males that have passed the test, and therefore they're more likely to survive, relative to something that doesn't have the trait and therefore hasn't passed the test. Well, somebody who hasn't passed the test may be good or bad, but we don't know. The female doesn't know. And here is the crucial point of the Fryer's paper. I'll let you read it. So you see, males, they were less likely to survive because they spent all this time and effort doing these dangerous activities, put their lives at risk. But they were more likely to be chosen as mates. Although you're more likely to die, you have more chance of passing your genes to the next generation. And that's why we are like that. So the 3 points of the Fryer's paper. Consumption of items with a negative survival value is a handicap. We pay a cost in terms of survival in order to consume these things. Utility maximization, maximization of a function of a combination of survival and consumption, is therefore similar, and this is what the Fryer shows, to the genetic problem of fitness maximization. Fitness is the number of, approximately the number of survival offsprings. And therefore, in this paper, the Fryer provides an evolutionarily consistent basis for our utility function. So that's where the utility function comes from, sexual selection. The analysis is quite complicated and the model is therefore quite rich in analytics, and I'm only going to sketch it. We think, the Fryer thinks of a sexually reproducing population where there are obviously two sexes, males and females, and here there's two specimens of the two sexes. Let them go away. Males have different qualities that differ in something which is good for female. They're better, they're stronger, they're more likely to resist parasites or illness, they run faster, and so on. The mathematical setup is a game theoretic one where every type, every male chooses his actions depending on his type. Type is this quality that is not observable to females and is important to females. And what are the actions? The actions are C and W. C is the investment in display activity. The number of teeth of a tiger that you are wearing. For example, Roman Abramovich spent a lot of money, not for him, but the point is this is a risky activity because everybody knows that the car VIP1 will be driven by somebody important and rich. W is the other thing that you can choose, and is investment in survival. Is eating well, finding hiding places, knowing where the animals are that might hurt you and hunt you, and so on. There's a trade-off between those activities. The trade-off is given by the production function. Okay, so there's a frontier, and if you have more consumption, then you must have less survival activity, and the frontier shifts out, hence the negative sign, with theta, with your type. The better you are, the more you can do in terms of consumption and survival. Survival is simply the probability of surviving to the next period, for the next year. Okay, so pi is increasing in the amount of activity that you undertake. Okay, so the analysis. This is the sketch of the model. The first part, there exists the signaling equilibrium. Now, signaling what? Remember, females are interested in a quality that is not observable in that theta. And you have to signal, males have to signal that they have a good theta. How can they do that? Because theta is a quality, and it makes it easier for good males to have more consumption. That's how they signal, by having more consumption. And here's the picture. Okay, so a low theta male will have low consumption, a high theta male will have high consumption. So if you know that you are this type here, then you will choose this consumption level here. And that's part one, the existence of this equilibrium, which is derived. Okay. Then the next part, the main result of the FRIA, is the equivalence of utility maximization. On this side of the diagram, I'm just giving you the diagram without the analytics. On this side of the diagram, we put the probability of mating, which is a good thing, and the probability of survival, which is also a good thing. And if we jot the points along this line, all these points give the same fitness in the sense of combination of probability of survival and of mating. Now there's a function g, the inverse of which maps every point in this diagram into points in this diagram. And what is this diagram? This diagram puts on the horizontal axis the type of the male, the quality, how good he is, and the amount of survival activity undertaken by that male. So for example, we have the red point here. This is projected by the function g minus 1 onto here. Okay? In other words, a male that has this type, theta A, and chooses WA as survival activity, will have a probability of mating given by the horizontal axis of this point, and the probability of survival given by the vertical axis here. Through the signaling, we know that this type theta will choose this level of consumption. We turn that with the 45-degree line onto this diagram, and therefore this red point here goes onto this red point here, which is on the axis we want, C and W, on the vertical and horizontal axis. If we take another point, for example the green one here, then we can do the same. This point will be projected here, and then it goes to that point. If we do the same for every point on that line, then we find an indifference curve, what we study in the first year or in the second year. If we take a better male, a male with a better value of theta, it will survive more for every probability of mating, and vice versa, will mate more for every probability of survival, and we have another indifference curve. And this is our indifference map. And what's the analytical description of this map? It's this one. Complicated enough, but has some features that we may want. First of all, it's decreasing, as drawn, and as we have drawn at school. We can construct utility in the arrow Debreu fashion by simply assigning a value to every combination of C and W. It's invariant to monotonic transformation. Okay, that's another feature that we study. But more importantly, according to the FRIA, is the fact that it's independent of the type. You don't choose your preference because you're good. You don't happen to like football because you're good at football. You don't happen to like broccoli because broccoli are cheap this year. The problem has to be well defined, so therefore we want our indifference curves to be convex, and this happens if the resource constraint is concave and the FRIA